Good morning. We are dealing with discrete communication channels, wherein we have to deal with these aspects, wherein we have seen in the first session how the channel is represented mathematically by way of channel diagram, channel matrix, and joint probability matrix. We have seen all the entropy functions associated with any discrete channel. We have studied about mutual information. We have studied about channel capacity and Shannon's theorem on channel capacity. So today let's look at some of the examples on calculation of channel capacity, and then we'll look at special channels. So let's look at calculation of channel capacity given the channel either in the form of a channel diagram or channel matrix. So there is a channel matrix here, P of I given X, okay, which is having 3 input symbols and 3 output symbols. Number of input symbols are 3, number of output symbols are also 3. Since M and N, number of input symbol and output symbols are equal, we can make use of Muraga's method to find out capacity of the given channel. So it's a fundamental relation. Channel matrix multiplied by some constants called Q is this transition probability log 1 divided by that, or log of that value. So 0.8 log 0.8, 0.2 log 0.2, 0 is 0 itself. Similarly 0.8 log 0.8 for this, and 2 times 0.1 log 0.1. So every row we take the transition probability, log up the transition probability, and add all these logarithms for a particular row of the channel matrix. So evaluation of this gives the values indicated in this matrix. So wherein left hand side remains the same here, and we have one matrix which is channel matrix and Q values, and these are the constants. So accordingly we can write 3 equations for this. 0.8 into Q1, 0.2 into Q2, okay, is equal to this constant value, minus 0.722. Similarly for the second row, 0.1 into Q1, 0.8 into Q2, 0.1 Q3 is this second constant. For the third row, 0.2 into Q2, 0.8 into Q3 is this third constant. And if you solve these 3 equations for Q1, Q2 and Q3, we arrive at the values. Q1 is this, Q2 and Q3 values. And in order to find the channel capacity in Muraga's method, the channel capacity is given by log of 2 power these Q values added, okay, to the base 2, gives out to be 0.8269 for the given channel, which is measured in bits per symbol. So if symbol rate is available, then this capacity is multiplied with symbol rate, that will give the channel capacity in bits per second. This is an example which is taken where the number of inputs and outputs are not equal. So if the number of inputs and outputs are not equal, then we can go with the conventional approach of okay, channel capacity is maximum rate of data transfer. Okay, with that concept, okay, we should evaluate if the number of inputs and outputs are not equal. So the channel capacity has the following character. The channel matrix, it's not capacity. The channel, a particular channel has the following characteristics. Given that, okay, the input symbol probabilities are equal, find the channel capacity if symbol rate is 1000 symbols per second. So channel capacity is given by maximum of this mutual information multiplied by the symbol rate, where the mutual information can be expressed as h of x and h of x given y, which we have seen in our previous class. So input symbol probabilities are given, so we are computing these entropy, which is 1 bit per symbol. Then we'll have to find out this h of x given by, for which we require JPM, joint probability matrix, and to compute this, we using this probability relation, we compute this P of xy, which is multiplication of channel matrix with the input symbol probabilities. Okay, so first row of the channel matrix elements are multiplied with P of x1. Second row of the channel matrix are multiplied with P of x2. So we arrive at the joint probability matrix. And then using this joint probability matrix, we can compute joint entropy and use the relations between entropy. We have this relation between various entropy functions. Using that, okay, h of xy given by h of y plus h of x given by, we want this h of x given by. So we have a joint probability matrix, joint entropy, and we require h of y. So h of y, in order to find out entropy of the receiver, we require received symbol probabilities, wherein using this property of JPM, adding the elements of the JPM column wise, we get output symbol probabilities. So if we add these elements column wise, 1 by 6 plus 1 by 12 will give us Y1. 1 by 6 plus 1 by 12 give us Y2. So this addition gives Y3 and Y4. So 1 by 6 plus 1 by 12 comes out to be 1 by 4, 1 by all these columns addition will lead to 1 by 4, 1 by 4, 1 by 4, 1 by 4. So this is the probability of Y1, Y2, Y3, Y4. Sum of all these will be equal to 1 or should be equal to 1. So entropy of the receiver is 4 times 1 by 4 log 4, which is 2 bits per symbol, and using that relation we can compute this conditional probability, which is h of xy minus h of y comes out to 0.9183 bits per symbol. So if we substitute this value, we get mutual information. H of x we got it as 1 minus the h of x given by value. This is what is I of xy, which is bits per symbol. So channel capacity is maximum of this value, since the input symbols are equiprobable, and we assume that the source matches with the channel. Okay, so this I of xy which we have got, okay, is max, and when multiplied with source symbol will give us 81.7 as the 81.7 bits per second as the channel capacity. So if it is not a symmetric channel, okay, if it is not the number of inputs and output symbols are not equal, we can go ahead with the conventional approach. If the number of inputs and output symbols are equal, like in previous example, okay, we can go for Morova's method. So given any channel, either in the form of a channel diagram, channel matrix, or JPM, we can compute the channel capacity, okay, using Morova's method if it is number of inputs and output symbols are equal. If they are not equal, we can use the conventional approach for any type of channels. Now let's look at some of the special channels. We have 4 different special channels. Whatever means the type of channel, the fundamental concept what we are studying here is, okay, obtaining the channel capacity of a given channel, and these type of channels, based on their behavior, we can categorize into 4 different classes. One is either the channel can be symmetric, or we can say it is a uniform channel. If it is a binary, then it is binary symmetric channel. Okay. This symmetric channel, if the number of inputs and output symbols are 2, then we call this symmetric channel as a binary symmetric channel. Then there is something called binary eraser channel, BEC, okay, and deterministic and noiseless channel. So depending on the behavior of the channel, a channel can be put into one of these 4 categories. Now for these different categories, okay, there can be a channel which is none of these 2. Okay, none of these 4 special categories. So for that, capacity of channel calculation is the approach that we have seen from the basic fundamental principles, basic fundamental definition. Now for these special channels, we are evaluating how is the channel capacity, okay, calculation process. So we will be looking at one by one. Symmetric or uniform channel. If you have a channel matrix P of y given S, this channel is said to be symmetric if elements of second and subsequent rows are same as that of the first row, where their location can be anything. If you have the elements of the first row as P1, P2, P3, so on up to Pn, right? Elements of the second or all the subsequent rows should be same as the elements of the first row, but their locations can be anywhere in that row. We call such, if the elements of the first row are repeated in all the remaining rows, okay, maybe positions changed in the matrix elements, right? Such channel, okay, represented in the channel matrix, we call it as a symmetric channel or uniform channel. For such a symmetric or uniform channel, where the second and subsequent rows are same as the elements of the first row, okay, irrespective of their position in a particular row. Okay, how to calculate channel capacity for such a symmetric and uniform channel, for which we are again making use of the fundamental concept, wherein one of the properties of the channel matrix is that the sum of the elements of any row is equal to 1. If you take a channel matrix P of y given x, okay, its property is that if you add the elements of one row, any one row, it will be equal to 1 or it should be equal to 1. So accordingly, if you look at this summation, for one row, okay, j is varying, okay, I is not there here, only for one xi, one row. If you add all the elements along one row, that will always be equal to 1. Accordingly, for a channel matrix given in this, okay, one row elements will always be equal to 1, for which the conditional entropy y given x for such a channel is given by, okay, the fundamental definition. And for this fundamental definition, P of this is split into joint probability is equal to conditional probability into P of xi. This is joint probability divided by probability of the conditioning event. So we have this joint probability here. So this joint probability is nothing but multiplication of conditional probability and input probability. So this input probability is taken out, and this is a joint probability, okay, for the given symmetric channel. So for this channel, right, we have this summation P of yj xi log 1 by P of yj xi. Right, if you look at this, is since all the elements of one row, okay, all the elements of the successive rows are the same. If you calculate this for one row, okay, that is this summation, which is represented as h, and that is constant for all the rows. Okay, this value is a constant. So h of y given x is this summation multiplied by, this is represented as a constant h, okay, a constant h, and this summation, sum of all the input symbol probabilities is 1. So channel capacity is given by maximum of I of xy, wherein, right, or since the mutual information is symmetric, we can also write I of yx. So yx is given by h of y minus h of y given x, right. So this is output symbol probability, h of y given x is h. So this channel capacity of a unit symmetric or a uniform channel is maximum value of h of y minus that entropy of one particular row, okay, one particular row of the channel matrix. When is this h of x be maximum? H of y will be maximum if all the received symbols are equiprobable. So when they are equiprobable, we have studied extremal property, wherein entropy is maximum when all the symbols are equiprobable, and that value is equal to log n to the base 2. Okay, total number of log of total number of symbol probabilities to the base 2. So channel capacity of a uniform channel is given by this maximum value minus that h value. H value is the entropy of one particular row multiplied by symbol rate will give us the channel capacity. So given a channel, if we can able to identify that it is a symmetric or uniform channel, meaning that all the second and all the successive rows elements are same as the elements of the first row irrespective of their location, then for such a channel, the channel capacity is directly given obtained using this equation, log n minus h into rs, bits per second. This is for uniform channel. So the example which we have seen in the previous case, right, has obtained Okay, its channel capacity is this is a channel matrix which we had seen in the previous case, right, where we have solved this example. Okay, we have solved the same example using the basic fundamental concept. Now, if you look at this, this is a symmetric or it's a uniform channel. It's a uniform channel wherein the second row is same as the elements of the first row with different locations. So, this given channel is a symmetric or uniform channel for which h of y given x is only one row, entropy of one row given by 1.1983 actually, right, wherein for such a symmetric channel, okay, channel capacity is directly obtained as log n to the base 2. 4 elements are there, okay, m and m is number of input symbols, n is number of outputs. So 4 log 4 to the base 2 minus this comes out to be 0.0817. Okay, if you take it that 3 here, it is 817, which is the same answer what we had got with basic fundamental calculations. If you look at 0.0817, okay, it is 0.918 was there. If you put that fourth digit also, it comes out to be 0.0817. So, if you can identify the channel to be a symmetric channel or uniform channel, then we can make use of this direct selection and estimate the channel capacity directly. This is about uniform channels. Second is binary symmetric channels. Okay. It is a symmetric channel, but the inputs and outputs are only two, hence it is called binary symmetric, right, wherein it is the one which is most commonly and widely used channel, type of channel, because the world is digital, the era is digital, and hence the type of channels or type of information that we communicate over a channel is generally binary in nature. So for such a channel, since the inputs are 2, outputs are also 2, and probability of correct transmission is indicated with P, probability of incorrect transmission is indicated with Q. Okay. So wherein its channel matrix is a diagrammatic representation for which correct transmission, 0 transmitted, 0 received, its probability is P, but 0 transmitted, 1 received is Q, 1 transmitted, 0 received, Q, 1 transmitted, 1. Correct transmission is P, incorrect transmission is Q, and sum of these two probabilities will always be equal to 1. Now, what is the probability of sending 0? That is taken as alpha, and sending 1 is of course 1 minus alpha. So for such a binary symmetric channel, again h of y given x is p log 1 by p, q log 1 by q, which is a constant. So here also, okay, it's a symmetric. Elements of the second row are same as elements of the first row. Okay, the only thing is the location is different. So for which entropy h of y given x is the entropy of only one row elements, which is h, and h of y, okay, channel capacity is given by maximum of h of y minus this h, and since this, when is this maximum? When the output symbols are equiprobable, and that will be given by log n to the base 2, wherein log 2 to the base 2 is 1 and this is h. So what we find here is channel capacity of a binary symmetric channel is 1 minus h. Okay, if multiplied by symbol rate, it is bits per symbol, where h is given by, okay, entropy of one row of the binary symmetric matrix. Okay. Third type of a special channel is binary eraser channel. Okay. Now here, if you look at, the elements are binary itself, transmitted elements are binary, received will also be binary. There is something called third value. Okay, we can think of this as a tri-state. Okay, a 0 state, 1 state, and this we can think of tri-state, neither 0 nor 1. So such type of channels are what we call binary eraser channels, wherein the transmitted information is binary in nature. Correct reception, of course, it is 0 and 1 binary, but incorrect reception is something called third value, neither 0 nor 1, which we can imagine that it is a tri-state value. For such a channel, okay, the corresponding channel matrix is 0 transmitted, 0 received is P, 0 transmitted, incorrect reception is Q. So there is no concept of 0 transmitted and 1 received. Okay, so this is always incorrect. So that probability is always 0. 0 transmitted, 1 received probability is 0. Similarly, 1 transmitted, 0 probability is also 0. Okay, incorrect transmission, okay, tri-state, like tri-state, that symbol is represented as Y, as small y. So correct transmission, 1 transmitted, 1 received is P. So for such a binary eraser channel, what is the channel capacity? When an error occurs, the symbol received is Y and no decision will be made about the information, but an immediate request will be made for the retransmission rejecting what has been received. Okay, we have seen in error correction methods wherein there is one option of correcting the errors in the receiver itself. Second option is if there are any errors, then we can request the transmitter to retransmit the same information until it is correctly received. So if Y is received, then an attempt is made to retransmit the same information again, rejecting what was received, thus ensuring 100% correct data recovery. And this is very much essential in case of transactions related to finance. Okay, there is no option for error. Okay, so in such applications, we can think of these kind of implementations. Okay, when it comes to finance type of very important data communications. Okay, so this type of binary eraser channels will ensure 100% correct transmission. Okay. Of course, there are limitations towards this as well, but what is most important is correctness of data delivery needs to be 100% in such applications, wherein we can think of these binary eraser channels. So BEC is also a symmetric channel with P of x is alpha, P of x equal to 1 minus alpha, for which again, okay, the elements of the second row are same as the first element. So h of y given x is given by the same, okay, and h of x here alpha log 1 by alpha and 1 minus alpha log 1 by alpha. Okay. We have calculated JPM, okay, comes out to be this, wherein JPM is this probability matrix multiplied by input symbol probabilities. Adding the elements, we get P of y. So h of y is given by entropy of these elements. We have calculated P of xy as well. Okay, dividing the JPM with the output symbol probabilities will give us conditional probability P of x given y. So h of x given y is entropy of all these elements. Okay, so that comes out to be Q h of x. Okay, h of x given y comes out to be Q h of x. So the relation I of xy, if you use this h of x minus h of x given y, right? H of x we already calculated, and h of x y minus y is, okay, 1 minus 2 h of x, right? Right, Q times h of x. So this is h of x given is Q times h of x. So h of x, if you take substitute this h of x given y as Q h of x, h of x minus Q h of x. So h of x is taken common, 1 minus Q h of x, and 1 by Q is nothing but P. Okay, probability of correct transmission. Okay, so mutual information is P times h of x. Okay, so this h of x, when it becomes maximum, the capacity is the maximum. That is the channel capacity. And when can this h of x be maximum? When the input symbols are equiprobable, and that is equal to 1. Okay, so channel capacity is simply equal to P when the symbol probabilities are equal. So P into symbol rate is the channel capacity of binary eraser channels. Straightforward equations. So given the channel, we should identify whether it is a special or uniform channel, whether it is a binary symmetric channel or binary eraser channel, and directly use these relations. Directly use these relations to calculate the channel capacity. Then fourth channel is deterministic and random channels. So it will be deterministic and noiseless channels. One is deterministic, other is noiseless channel. So let us first look at what is meant by deterministic. Right? We have a channel matrix like this. When we say that this is a deterministic channel, okay, hope you can understand deterministic, determinant, we can definitely determine, okay, that is called deterministic channel. Okay. A channel is said to be deterministic if each row of the channel matrix contains one and only one non-zero entry and all other elements must be 0, and that non-zero entry should be equal to 1, because if you add the elements of one row, that should be equal to 1, and we say that it is a deterministic channel if there should be only one non-zero element in that row and that non-zero element must be 1 with all the remaining elements 0. Okay. So all the remaining elements 0 means such a reception is not possible, and the only reception possible because its probability is 1. Okay. So that is why it is called a deterministic. That is, the channel matrix is symmetric and has a property of y given a, p of y given x is 1 only for a given I and j. For this transmission, this is a reception, no other reception possible. Okay. For such a channel, h of y given x is always 0. So I of xy is simply entropy of the receiver. Okay. And the h of x and h of y need not necessarily be equal. So example of a deterministic channel. In a particular row, one and only one element must be 1, remaining all zeros. Okay. And that is the corresponding channel diagram. Deterministic. So for which the channel capacity is given by maximum of I of x. So maximum of x of h of y, and this h of y becomes maximum when the symbol probabilities are equal, given by log n to the base 2. So when we say that it is noiseless channel, a channel is said to be noiseless if the channel matrix is a square matrix and all the principal diagonal entries are 1 and remaining all entries are 0. Okay. Noiseless channel. This channel matrix is a square matrix wherein number of input symbols and output symbols are. So in this case, it m and n are equal, right? Wherein only the principal diagonal elements are 1 and all the entries are 0. Only principal diagonal elements are 1 with all the elements 0. Okay. So noiseless. There is no concept of noise and receiving incorrect output. So if x1 is transmitted, it is received as y1 itself. Okay. And all other probabilities are 0. Such channel we call it as noiseless channel, for which if you look at p of x given yj comes out to be 1. Okay, and this p of x given yj is 0. Okay, all these probabilities are 0 for I not equal to j. All upper elements of upper part of principal diagonal, lower part of principal diagonal, they are all zeros. Okay. So for such a channel, how is the for such a channel? If you look at the channel capacity for such kind of channel, right? P of x given y and y given x are the same. Joint probability, input probability, and output probabilities are same. So because of which h of x is equal to 5, y of x is equal to 0, and all these are equal, and that is what is mutual information. Okay. So for a channel to be noiseless, it is necessary that there shall be a one-to-one correspondence between input and output symbols. No information is lost in such channels, and if all symbols occur with equal probability, it follows that, okay, these are maximum values, and that is a channel capacity. Okay, either it is log of n or log of m, because it is a square matrix. So these are the four special type of channels, okay, and their corresponding channel capacities we can make use of direct equations, right? So given the channel represented in the form of channel diagram or channel matrix or JPM, our objective is to calculate channel capacity, and to calculate this channel capacity we require their entropy functions and mutual information, right? And for the special type of channels, if you apply that basic definition, right, we can directly arrive at the final equation and use that equation for that special type of channels for the calculation of channel capacity. So the fundamental thing that we are studying in this unit is calculation of channel capacity for a given channel, represented in the form of a diagram or channel matrix or JPM. That is the study related to this unit, wherein we have thoroughly covered all the aspects related to discrete channels. So overall, if you look at the digital communication block diagram, if we look at this digital communication block diagram, in the first unit we have studied source encoder, okay, with without memory and with memory, and for each one of these type of sources, right, how to calculate entropy and entropy rate, that we have studied related to source in unit 1. We have studied the fundamental properties every source code should have, and accordingly we have studied 3 algorithms that satisfy all these 5 fundamental properties of source coding. We have studied binary encoding algorithms, Fano and Huffman algorithm, which generate source codes, and then followed by we have studied channel encoding, wherein to enable error detection and error correction, right, we have introduced some extra bits called check bits using linear block code, and these check bits are interleaved in the message using convolution operation called and such encoder we call it as a convolution encoder. That also we have studied as a part of channel encoding. So all these 3 blocks, okay, this is unit 1, this is unit 2, and this entire block, okay, will cater to unit 4 and 5. Followed by the modulator is studied in digital communication in 5th semester, and now we have studied the mathematical modeling and calculation of channel capacity of this channel. And all these demodulation, decoding processes, they are the reverse process of what has been implied for transmitting part. So in total, considering the 5th semester digital communication system and 6th semester information theory and coding system, coding theory, The entire digital communication is studied thoroughly, and we have studied lot many parameters associated with each one of these blocks. So thereby the thorough knowledge of these two subjects make us enable to design any digital communication system for a type of application. Okay? And that is what is the content of the subject related to digital communication system, which we have studied in two different subjects. One is the modulation demodulation part in digital communication in 5th semester, and in 6th semester about the discrete source coding algorithm, channel coding algorithms, and then mathematical analysis of channels in ITC, information theory and coding. And that is what is the content of this semester in ITC. Hope you all have understood thoroughly the aspects of each one of these blocks in a digital communication system, and hope that you are confident to design any digital communication system, both transmitter as well as receiver part. So still go through all these contents thoroughly, analyze them. Any queries, you are free to interact with me for clarification of doubts or any further study. Thank you very much, and wish you all the best for all your upcoming events. Thank you.